So this is our short video lecture that we didn't get to finish on Friday the 27th of January 2017. This will be a brief synopsis on how to decide substitution versus elimination, namely SN1 or E1 versus SN2 or E2. In general, primary and secondary alkyl halides will undergo only SN2 or E2 reactions. Remember, this is because primary and secondary carbocations are too high in energy to undergo a non-concerted stepwise pathway. Tertiary halides will undergo either E2 or E1 or SN1 depending on the reaction conditions. Our first example here, where we're going to examine the electrophile followed by the nucleophile, we have our tertiary butyl bromide, and we have a strong base, and we would say that this is also concentrated methoxide. So we would predict that methoxide would pull off the beta proton with concerted loss of bromide ion to give you the E2 elimination product, isobutylene. Alternatively, if you used a weakly basic solvent, which is also the nucleophile, the tertiary alkyl halide will undergo SN1 and or E1. In general, our author states that if you heat the solvent for longer periods of time, that due to the increased entropy, you would expect the E1 process to predominate. And if you were to run this reaction at lower temperatures, you would expect the SN1 process or the SN1 product to be the major organic product. So, our relative reactivities of alkyl halides in SN2 and E2 reactions are that primary alkyl halides react the fastest in SN2. And we saw again that tertiary alkyl halides do not undergo due to their steric hindrance, and that the nucleophile cannot approach backside, that is 180 degrees to the leaving group. E2 eliminations are fastest with tertiary alkyl halides, and therefore we could say that E2 is favored in tertiary, and alternatively primary favors SN2 reactions. Secondary alkyl halides are sort of up in the air, so you have to juggle the reaction conditions and the steric nature of both the electrophile and the nucleophile. So here's another example where we deal with a primary alkyl bromide, 1-bromopropane, and here we've chosen a good nucleophile methoxide. And because we said that the rate of SN2 is fastest for primary, we would expect that the 1-methoxypropane would be the major organic product via the SN2 pathway. So here's our summary for SN2 versus E2 of primary alkyl halides. If a primary alkyl halide or a nucleophile is sterically hindered, there's greater difficulty for the backside displacement at the alpha carbon, and so this will stack the deck to favor E2 elimination. So here we see that we have the same methoxide nucleophile, which is also a strong base, but now we've placed a branched methyl group at the beta carbon, which makes it slightly more difficult for the methoxide to approach backside of the leaving group. So here we see that we have competition for the E2 pathway, and our SN2 product is now only 40%. Neopentyl bromide, with even greater branching, does not undergo SN2 reactions at all. And you'll note that there are no beta hydrogens, so there's no elimination. Here we have still the less sterically encumbered primary alkyl bromide, but now we have a really bulky base, so we would say that this is relatively non-nucleophilic tertiary butoxide. So here again we would only see mostly elimination products via E2. So now if we move on to secondary alkyl halides, comparatively a secondary alkyl halide reacts slower in an SN2 reaction and faster in an E2 reaction. So therefore we would expect both products. the relative amounts of SN2 versus E2 products depend on the strength and also the steric bulk of the nucleophile / base. In general, the stronger and bulkier the nucleophile base, the greater the percentage of the E2 product. So in our first example, isopropyl chloride, the secondary alkyl chloride, plus acetate, which we would consider a moderate nucleophile and a weak base, would give us 100% substitution product via SN2. And remember, there's no SN1 because we would not generate a secondary carbocation. If now we use a relatively small, strong base, and if we increase the concentration of ethoxide, we would expect E2 to predominate of this secondary alkyl chloride. If we use azide ion, which is a bullet nucleophile, it's linear and it has a negative charge, it's a really good nucleophile, and it's also a weak base. The pKa of the conjugate acid, hydrozoic acid, is 4.6. Similar to the pKa of acetic acid, 4.76, we would expect only SN2. Secondary alkyl chlorides continued. Now a bulky base, remember, favors elimination. So if we move on to a bulkier base like DBN or DBU, we would again see elimination as the major product. And don't forget that if you have alkenes with branching at the beta carbon, we would expect the less substituted alkene to predominate due to the steric hindrance of that beta proton on the more branched carbon. Similarly, pay attention to alkyl chlorides or alkyl halides in general that have a gamma alkene, because you'll want to watch out for conjugation. High temperatures favor E2 with secondary alkyl halides. Our author explains this in terms of greater entropy. E2 produces an alkene plus a leaving group and the conjugate acid of our base, whereas SN2 produces only two products. So for example, if you heat isopropyl bromide at only 45 degrees with hydroxide ion as both your nucleophile and your base, we see roughly the same amount of both substitution and elimination, SN2 and E2. However, if you then take the same reactants, but you heat them to about 100 degrees, we see that hydroxide acts primarily as a base and favors E2. So here we've stacked the deck and we get 71% of the E2 propylene product and only around 30% of our substituted product, isopropyl alcohol. So our summary is that secondary alkyl halides undergo both SN2 and E2, but if you have a strong, bulky base and high temperatures, E2 elimination will be favored. Now on to tertiary alkyl halides. Tertiary alkyl halides cannot undergo SN2 reaction. They're too bulky for the nucleophile to approach backside of the leaving group. Only E2 products are formed from tertiary alkyl halides plus a strong base. So if we examine this tertiary butyl bromide plus ethoxide, the strong base, E2 is observed and we produce isobutylene gas. Now what about SN1 versus E1 of tertiary alkyl halides? These are both possible when they are reacting with poor nucleophiles and weak bases. So remember that tertiary alkyl halides' first rate determining step is cleavage of the carbon leaving group bond to form a tertiary carbocation. At this point, the strong or the moderate or poor nucleophile can then attack the positive formal charge and give you your substitution product. Alternatively, the weak base may pull off your beta proton, and in general it would attack mostly beta prime to give you the Zaitsev more substituted and therefore more stable alkene product. And remember, that's the same for E2 elimination. We in general see the more stable alkene, or that is to say the more substituted alkene, and if you have a possibility for E and Z diastereomers in general, the larger groups are disposed on opposite sides of the double bond, that is E. Primary and secondary alkyl halides do not undergo SN1 sovolysis or E1 reactions because primary and secondary carbocations are too high in energy intermediates. We've repeated this several times. But remember that the tertiary carbocation is relatively more stable, so we can see that this unimolecular pathway is favored. So after formation of that tertiary carbocation from the tertiary alkyl halide, the SN1 product is favored because no other bonds need to be broken at lower temperatures. So if we take this tertiary butyl bromide in ethanol at 30 degrees, we will observe that 81% of it is the SN1 substitution product, whereas only around 20% is the E1 isobutylene gas elimination product. Now remember, if you had chosen instead of ethanol its conjugate base, the strong base ethoxide, it would give only the elimination products, and that is via the E2 pathway. So for tertiary alkyl halides, you have to gamble between SN1, E1, or E2. So here's our summary: substitution versus elimination. For primary alkyl halides, they undergo primarily substitution reaction unless there is steric hindrance in both the electrophile and or the nucleophile, then this would favor elimination. Remember, primary alkyl halides cannot undergo SN1 or E1. Secondary alkyl halides may undergo both substitution and elimination. The stronger the base and bulkier the base, and higher the temperature, the greater the percentage of elimination will occur, E2. Remember, secondary alkyl halides also do not undergo SN1 or E1 reactions. Tertiary alkyl halides may undergo E2, but they may not undergo SN2 reactions, again due to steric hindrance. Tertiary alkyl halides may undergo SN1 or E1 reactions, depending on the reaction conditions. In green are highlighted reactions for primary alkyl halides. The first, primary alkyl bromide. If you have a relatively low concentration of methoxide, you'll observe SN2 as the major product. And remember, SN2 is very fast for primary alkyl halides. On the other hand, if you use a bulky base like DBN or DBU, you'll get only E2. And here we see that the proton, the beta proton, was eliminated from the less sterically hindered beta carbon. There is no SN1 and no E1 with primary alkyl halides. If you have a branched, more sterically hindered alkyl halide that's primary, and you have a higher concentration of methoxide, you see that we get mostly E2 elimination. Onto secondary alkyl halides. If we take isopropyl chloride with a moderate nucleophile, we see substitution. With a strong nucleophile like methane thiolate, we see substitution via SN2. Strong nucleophile like azide and cyanide, which are small and linear, we also see backside displacement to give primarily SN2 products. If we have a larger concentration of ethoxide base or a bulkier base or hydroxide at very high temperatures, we see E2 elimination as the primary pathway. Tertiary alkyl halides, if you have a negatively charged strong base, you'll see E2 elimination. And if you have a moderate nucleophile and a weak base, which is generally the solvent, and you have lower than reflux temperatures, you'll see primarily SN1 substitution products.